Okay, today we'll continue our discussion with reinforcement learning. In particular, we'll go from deep Q networks to policy gradients to the active critics algorithms. So here we go. Well, let's review. Last time we're talking about the Q learning value iterations, and this formula look complicated. It's really not. You have a new Q value that basically can calculate from the old Q value times the learning rate plus the rewards and a discount factor multiplied with the max Q value would correspond with the best actions and minus the old Q value, right? And you keep updating this table with all the possible state and all the possible action and the pseudocode that we see last time. Now, if you look closely, the problem with this kind of approach is that it might work with a small Q table, but if you have a really large Q table, then it becomes very sluggish and slow and sometimes not even possible, right? So keep that number of state and number of action in mind as we go forward here. So representations matter. Value iteration is impractical for large number of action and large number of states. And for some problem, you cannot generalize to an observed state. Say you don't know what state that is because of the uncertainty of the environment. That's another issue. So let's be very specific about a game playing problem. Say you're going to play Breakout. And so the state will be the screen pixel with what the computer sees here. And the image size, maybe we resize into 84 by 84 image. In order to know the action, you construct a consecutive 4 images in the row or 4 frame. And say we only have grayscale images with 256 grade level. Just simplify the problem into that. But the possible number of state would be 256 powered by 84 by times 84 times 4. So you have that many rows in the Q table. In fact, if you do the math, it turned out to be so much larger than the total number of atoms in the universe. If you do the math, 256 powered by 28,000 here. So it's not very feasible for us to construct that Q table with all the possible states. So how are we going to do it? We're going to use a neural net. And instead of compute the Q table directly, we're going to just approximate the Q table, right? That's the whole point of Q network. And so let me look into it real quick. So instead of putting both state and the action in the Q network and calculate the Q value, we're going to do something slightly resembling a neural net. We're going to feed in the state, which is the pixel, and then we're going to approximate the Q network by saying, okay, given this state, what are the Q value of taking action 1, 2, all the way to n, right? And this is more manageable because the number of action you can take typically a lot smaller than the number of states that are available. So this architecture closer to what we learned so far in the neural net, and it's also more manageable with the number of action, right? Okay, so that Q networks right here in that assembly of different algorithms. Okay, so Q network trying to approximate the Q functions and uses it to infer the optimal policy, in this case, pi of S. And you see here, feeding the state, the deep Q network would basically generate different Q value given the state and for each of actions, right? So for example, here, given this screen, I will give the Q value for taking action A1 is 20, A2 is 3, and A3 is 0. A1 means you move left, A2 you do nothing, A3 you move right? So for a breakout game, there are 3 possible actions that you can do. And then the optimal policy basically just taking Rmax of that Q function. In this case, A1 would be picked. Simple enough. All right, how do you train the network? The loss function that we're going to use is this. It'd be the expected square loss, right? So we've seen this before. Now this calculates slightly different. So this Q value is the predicted value. You've seen that. And this one is what called the target, is what you want to shoot for. And this interesting about this target is that you kind of infer to the Q function that we learned earlier to calculate the target. So in particular, you're going to look at what is the reward for the current action and the future reward with some discounted value and a maximum Q value for taking the best action, right? So in order to calculate this, you need to move to a new state, right? Because this is the future state. So you have the state X, S prime here. So what happened here, you want to do this, you have to pass the signal again through the network to calculate it, right? So you see what you're doing here? You're trying to calculate the loss by passing second time to the network, right? With a different state here, or the next state. So in order to do this, you either use the same network for both Q function, or you can use double network. So one network calculate what you're trying to calculate now, and then the other network separately to reduce the bias introduced by the inaccurate Q network at the beginning of the training. So this is really a design choice, but you can see why you need two of them, right? Okay, so let's look at one particular architectures, and this is from the paper by Manil and others called Playing Atari with Deep Reinforcement Learning. This is back in 2013. The network is actually quite simple. You probably can really recognize this. There are a 3 level of convolution. Each of them run on different filter size and also different number of filter. They all use ReLU. And they basically narrow down the network into something more manageable and then feed it into a fully connected layers. In this case, 512 and then 18 layers. And at the input and the final is that you map it into the number of action that you can do here. Remember the joysticks you have either just the direction of the joystick or combination of the button. So you map into this at the final results. Pretty cool. So you know the action given any screen pixel input. You now have figured out how to play the game. Right. So another really cool trick called experience replay. You might have heard this mentioned in the generative learning lectures. But to look at this loss function again. And the problem here is that the current Q network parameters determine how the training progress. So you use the current state to determine how the training progress. And this is kind of problem because of bad feedback loop, right? Say you have a really bad Q network parameters, and then you're going to use it to determine how the training progress. So it basically makes the training worse, right? So to avoid this problem of bad feedback loop, what you can do is that you can store the experience. And the experience is a set of actions, transition, and rewards. And then create mini batch for them during the training process. And what you do is you continue to update this what called replay memory table. So you can create like a replay buffer, and you start feeding continue game experience as you play. And you're going to update the Q network based on this random mini batch of these transitions of replay memories instead of taking consecutive samples, right? So in this case, all of your training sample will be randomly from the experience replays, not from directly generated by the current state of the Q network, right? So this helps a lot with the WQ network. So let me watch the videos here. The demo, and the video kind of long, so I'm gonna fast forward a little bit, but basically show how they'll play the breakout. So first training, it's kind of did really terrible. It missed all of the point, but it kind of moved things around a little bit that you can see it didn't really do anything well. And then after 120 minutes of training, it started learning how to play the game a little bit, so it knows how to move so that the game keep continue with the different frames here, and it start playing the game. And after a while, it start playing really well. In fact, you can see here it's gonna just continue playing the game, winning all of it. And let me show you a trick that it does. You can see what a trick it does here for expert gameplay for breakout is that you're trying to get up here. you're gonna get the ball up here, so it starts winning all the thing without you doing anything. So that's what we're trying to do. Eventually, you're gonna trying to get up to the size and up here, right? So that was the pinnacle of gameplay there. And so they did this experiment on all the Atari game and how the DQN perform against the best human players. And you look at this line, this is all the games, and look at this line. Any game above this line is that the DQN surpassed the human level performance. So for all the gamers out there, you got a challenge, right? But there's some other game that's not doing as well. So you can look into details of the games here, but you can see in that many games it was able to beat the human performance. Now, Q learning not without any downsides. So number one downside is that if the Q function is too complicated, you can have a trouble approximated. Especially Q functions are built on the multidimensional states, right? So for example, in robotic application, you have a lot of different degree of freedom. In that case, it's gonna be hard to approximate a highly dimensional Q function. Also, because the Q learning make everything discrete, right? The state had to be discrete, the action had to be discrete. It will not designed to handle continuous space. And finally, it's deterministic. What it means is that it directly compute from the Q function, and it cannot learn stochastic policy or random policy. So if the environment is uncertain, it won't be able to account for those, right? So certainly you can try to do an exploration versus exploitation as a trick, but the algorithm itself do not have any stochastic sense built into it, right? So can we do better? Can we optimize that policy pi directly and then find the best policy from a set of policies, right? So that gives rise to the next level of reinforcement learning called policy learning or policy gradients. So the key ideas here is instead of approximating Q and inferring the optimal policy, we're gonna learn the policy directly. We're gonna directly optimize the policy, right? So given the state through the network, we're gonna learn the probability of each of the action given the state. You notice now it's not the Q table anymore. It's not the Q learning anymore. It is a probability, which is more natural to neural network anyway. So you think about it, this is just a probability of each actions, and they all sum up to be 1, right? So you can think about it like a softmax or over different kind of actions here, right? So this is, think about each of the action is like the class that you're trying to categorize or classifies. Okay. So the advantage is, okay, if you have discrete action space, then you can do something similar to DQN. So basically to have a breakdown of different actions and then the probabilities of doing what. Really high probability moving left here, lower probability, even lower probability moving right. So you know that you should move left in this case. But the nice thing about this is you also handle continuous case. For example, instead of moving left, right, or stay still, I now have a continuum spectrum. What does that mean? It means I can infer to the velocity in which I want to move in certain direction, right? So here I show you negative 0.2 meter per second. What does that mean? It means that I continuously move to the left because this is negative. So you can think a negative in move to the left, positive move to the right, and it's meter per second. And you can change it dynamically. It's a smooth transitions, right, in action space, which is really, really nice. So now instead of learning sort of a discrete distribution here, you learn a smooth, continuous distribution of the action space, and then you can sample from it to make your decision. So it support continuous action space here. All right. So what happened here is that what the network would learn is what is the mean vectors and the variance, right? And then from there you can sample an actions, right? In this case, the action is to move negative 0.8 meter per second, which is move to the left. Right. Cool. So for the formulations, we define a class of policy, big pi here, that include all the policies and parameterized by the theta. Theta is the network parameters, and theta is in the space Rn. And what you're trying to do is trying to optimize a value called discounted future rewards. You know this value from the last lectures, right? So it's expected value of the discounted. So you have a discounted factors here with all the future rewards, right? So the sum of all the future rewards given a certain policy, right? The current policy that you're in. And then you're trying to find the optimal policy by maximum this rewards, right? You had a maximum of the rewards, right? So it kind of feels strange a little bit to you because when you think about it, we typically denote J at the loss function, and you're trying to minimize it. So this slide, you're doing quite the opposite, right? You're doing maximization instead of minimization. But we know for numerical reason, if you want to do maximization, all you had to do is flip the sign for the minimization, right? Or in the other words, you can try to maximize the negative loss. It's the same thing as minimize the loss, right? So in this case, you maximize the rewards, same thing as you minimize the loss. So how do you do this? The go-to answer is gradient descent, but in this case, it's gradient ascent, right? Because you want to move the parameters to increase the rewards, not minimize the loss, right? So that's the name that give rise to the name policy gradient, right? Which is lambda of, or gradient of the function j here. Okay, so let me show you an example of playing a pawn game, and this is a paper from 2016 by Andrei Karpathy. And to note that Andrei Karpathy actually go on and become the director of AI at Tesla. So he's quite up in his game as well. All right, so let's see this video. Okay, so pawn game, quite simple, only up and down. So you can approximate the probability of moving up, right? And that's the only note that you need. So down is just 1 minus probability of moving up. And then you feed in raw pixel and you go through hidden layers. And then you have this output, right? They train using 200,000 pawn games. And the really cool about this application is that all it see is raw pixel input. It don't really literally see anything else. So this is a step toward general purpose AI, because you see there's nothing else, just the raw pixel, a neural network, and the probabilities. Right? So it was about to play not very, it's really jagged, but it's also really fast. So it was to play really well against like a human, winning for the most parts here, right? Well, what's the problem here now? The problem here is that the training had to wait until the ends to get the reward of the outcome. So you go through a series of actions, and then you determine the outcome at the end, like whether you win or you lose, right? And each of the action here that you have feeding at also have a state feeding into it. So what you do is that you run in simulation certain policy for a while, and then collect the state action rewards and combine it into what called an episode. And what you do is, if you see a high reward, then you increase the probability of those actions inside that episode. If you see that it lost or no rewards, then you decrease the probability of all of the action inside the episode. Episode meaning all of these series of action, right? So you calculate the J function now is using this formulation, and you have the negative here is because, remember, you want to maximize rewards, and if you put in the framework of gradient, it's the same thing as you want to minimize this negative rewards, right? So you want to minimize the negative rewards. That's what the minus sign is here. And then you have a log of likelihood with the probability of taking a certain action given the state, right? And this one, you multiplied it with the discounted rewards that we mentioned is from last slides. So that's how you calculate the function J here. And the network parameter will be updated just like our old friend gradient descent, updated by minus the moving opposite of the gradient of the cost functions here by some learning rate. And because it's negative here or minus here and negative here, you think about it is a positive sign. And then you to plug J from here down to this equation, and you end up with this policy gradient. So that's how you update your neural network parameters at the training progress, right? So can I have some pseudocodes here for you? It is a reinforced algorithms, and the step basically trying to implement these functions here, and collecting information from each episode and then update the network accordingly, right? So this algorithm called reinforced algorithms, if you want to look that up or look at the implementation. But the pseudocode is pretty straightforward here. I'll just show you. Well, the issue with policy gradients is what I've just actually shown you earlier, is that you had to wait until the end to determine the outcome of the actions, right? So you have serious action here, it could be good, bad, but you can't just take it immediately after you take an action, but you had to wait until the end, right? So if the rewards is high, then you judge that all the actions as good, even though some of the action in there was bad, right? So for example, if the outcome of this is good, you would think every action here is good, but this one actually bad, right? So there is some issues there. And a consequence, though, you have to have lots and lots of training example to have an optimal policy. This also means that the training will be slow, because what happened is one action, some Siri will think is good, and then same action, another Siri will think is bad. So you increase and then decrease it. So you keep oscillating for some action, and it wasn't, it was very slow to learn whether it's a good action or not. And it takes a long time to converge, right? So if you compare PG or policy gradient to DQN, there is some pros and cons. The pros is that it doesn't care about the Q function anymore. Even though the Q function is very complex, it can still learn a good policy. It's, faster to convert compared to DQN. It is stochastic, whether DQN cannot do a stochastic policy. And finally, it supports continuous action, right? To model policy gradient on the continuous space. Well, what's the other cons then? The cons are, it's sample inefficient, which means that it need a lot more data in DQN to train, just because it needs a series of action, and there is a lot of back and forth between, higher, lower probability of those actions. Stability, same thing. It's less stable during training process, because if the action probability keep oscillating up and down, it be hard to determine what is the right action. And as far as the credit assignment, it is a poor assignment to the action and state pair that delay the rewards, right? So that's the delay is the keywords here that you can't see the reward until the end of the series of action, right? So, can we do better than that? Can we update at each step instead of delay until the end, right? And the answer is yes. And that gives rise to the hybrid method called actor-critic algorithms. Okay, so what is actor-critic algorithms? You're going to use two neural networks, an actor and the critic. An actor will control which action to take, and this follow a policy-based network, that's what we talked about earlier. And then the critics is going to measure how good that action is. So for example, if the actor rotate a piece, the critic would say, really bad action, or really good action, or okay action, and so on. And the critic going to be on value-based, a DQN value-based network, right? So these two going to play with each other, reinforce each other to become better, right? So in the way you can see there's some spirit of the adversarial network a little bit there, right? So if you make some connection, that's one of the connection you could make. This could be George and David there, right? Generator, discriminator. But slightly different settings here, right? So the design is that the actor will decide what action to take using the policy gradient. And then the critic tell the actor how good the action is and how it should adjust using a DQN. And so this is kind of alleviate the task of the critics that it's only have to learn the value paired generated by a policy and not you don't have to learn that directly. And this also can incorporate some of the Q learning tricks, such as experience replay, exploration, exploitation, and so on, right? And that depend on what algorithm that you use. There is a class of algorithm called advantage actor critics, and they calculate the advantage function. Basically define how much an action was better than expected, and here's the formulation of it. And again, this is the advantage. Advantage are given by the difference between the reward by the actor action versus the expected rewards, which is predicted by the critics. So you can think about it like the critic would say, okay, it's going to be this good, but you turn out, if you evaluate it, it turned out to be much better, right? So if it's much better, then you have a positive advantage. But if it's not, then you have a negative advantage or a disadvantage. So you're going to calculate the rewards based on this formulation, right? Notice the reward by the actor action is calculated by the current rewards plus the reward in the future. But this reward in the future are not predicted by the actor network, but predicted by the critic networks, the phi networks here. So just so you know that it also depends on the critic to predict the actor action in the future, right? So we're using this advantage function. The gradient becomes just the gradient of the log likelihood of taking this action under this policy times the advantage function. Right? Okay, so I fostered this pseudocode. This is steps for you to do the advantage actor critic algorithms, or the ACE2C. You take an action, you get the set of state, action, next state rewards into an episode, and then you update the critics, right? So your critic need to be trained here using the target of the outcome of the actions here. And then you evaluate the advantage functions using the formulation that we see from last slide, and then compute the gradient, basically just the log likelihood times the advantage function, and then you update the weight based on the gradient. Similar to what we've seen before, right? There is a couple of design decisions here. You can use a two-network design, one for the critic, one for the actor. And the plus side is that it's really straightforward and simple for thinking purposes, but it also doesn't share any parameter or feature between the actor and critics. So as an alternative, you can use a shared network design. So all these are shared parameters, and both of the networks take in state and input anyway, so it can be shared. And for the shared network design, at the end node, you're gonna about half of the node output would represent the critic, and about half of the node would represent the actors. So the design decision really up to the designers here. Okay. Lastly, we're talking about application of reinforcement learning, and I was teasing you from last video in the game of Go. So let's see how it does in the game of Go here, right? In the game of Go, many of you may be familiar with it, but many of you may not. So the game of Go, the purpose is to control as many territory as possible, and by surrounding your exponent, right? So if you have exponents here and you're able to surround him, you now control that territory, and no exponent can be, or all the exponents are going to be expelled from that territory. And so it's a pretty cool game. It's very popular in Asia. And the state of the game can go from really simple. If you increase the size of the game, the number of possible game position increase exponentially. And if you go to 19 by 19 board size, which is a standard one, the legal game moves many times exceed the number of atoms in the universe. So you think you cannot possibly generate all the states of the games here. So AlphaGo is an application that uses machine learning or reinforcement learning by DeepMind to train how to play Go. And they execute it through 3 different stages. Phase number 1 is initial training. So they're collecting data from the professional Go games, and from there build a supervised learning policy network. Right. So these are, think about it like they're gonna build like a critics network. And then the phase 2, they're going to use a actor critic framework using cell play, and they just keep playing with themselves with the policy gradient. Win, you get +1, lose, you get -1. And so potentially they can generate unlimited number of gameplays using the cell-played actor critic framework. And then using the self data, they're going to build a regression network to have a value network. And they're going to combine the value and the policy networks in a Monte Carlo tree search algorithm to determine what is how good is the current state and how to take the next action by using a look ahead search. Right? The detail, you probably want to read the paper for all the nitty gritty detail, but these are main 3 phases of the network. Okay, it's been through a journey to beat the best Go players. Starting in 2015, it started beating other world champion, and in the March 2016, it beat the top player in the past decade, Lee Sedol, 4-1. So, at least Lee Sedol won one game, right? And if you watch the documentary, you can see how dramatic this becomes, and capture this shot here at how frustrated Lee Sedol was playing with the machine. I would not play with the machine. It's no fun, right? I want to play with another human. AlphaGo have various variants here. AlphaGo original in 2016 require many engineering tricks, human gameplay, add training data, and the beat the 18-time world champion Lee Sedol. AlphaGo Zero in 2017 simplify and also become a more elegant version of AlphaGo. No longer need the human gameplay. It's trained from scratch, and it beat at the time #1 world champion. And in 2018, DeepMind released Alpha Zero, which is a generalized version of AlphaGo Zero, and it can generalize on other games such as chess and shogi as well. So here's some performance result of AlphaGo here, Alpha Zero, I'm sorry, and it's beat the Stockfish, which is the most powerful chess engine. So from knowing nothing about chess and just collecting directly training data and cell play, it was able to beat the best chess engine. About 13% of the time. And notice that they draw a lot, right? In chess, if both player was so good, you end up with draw. So that's why you have the gray bars here. But the Alpha Zero would win most of the time, and same with Yogi and Go here, right? So, in summary, we learned a few exciting algorithms in the reinforcement, and it kind of build up on top of each other. So it's really nice to see the progression of reinforcement learning. We learned about the value-based deep Q network to approximate Q function and infer the best policy. We learned about the policy-based policy gradient to learn the policy directly, and a hybrid method actor-critic algorithms where the actor decide what action to take and the critics tell the actor how good the action was and how it should be adjusted. Right. So next, and we also show you some application in AlphaGo and AlphaZero. Next video, we will talk about the implementation of reinforcement learning using a library called TensorFlow Agents. Until then, take care.